Hello and welcome to the Operations Research course. This week I'm going to talk about sensitivity analysis. So previously we have done this analysis to an example that has two decision variables, such that we may perform the sensitivity analysis graphically. However, if we have more than two variables, of course, we cannot do it graphically. So this week I'm going to talk about how we are going to use the notations and formulas that I have introduced in the previous week, and we're going to use all those notations and formula to perform the sensitivity analysis. So let's start. So first of all, when you would like to perform sensitivity analysis, you need to make sure that you have obtained the optimal solution. Okay, so remember that you need to solve the problem first, you obtain the optimal solution, and after that, you may perform sensitivity analysis. Okay, so you get the optimal solution first, and then you know the optimal basis. So you know which basic variables are, the basic variables in the optimal solution. And then you start analyzing if there's a change in the parameters. Check if that change will keep the current basis optimal or not. So for maximization, this is what you need to do. First, using the optimal table and the notation and formula that I've introduced in the previous week, you see how the change that you make affect this optimal table. Specifically for maximization, we check if each variable in row 0 still has a non-negative coefficient, and then the right-hand side of each constraint is still non-negative. If this is the case, then our current basis is still optimal after the change. However, if any of these two is not satisfied, it means that our current basis is no longer optimal. So here's an example of the optimal table for Dakota problem. So we have S1, X3, and X1 as the basic variables. So in the previous slide, what we need to check from this optimal table is that if we make a change in the parameter, then we need to make sure that the coefficients for all variables in row 0 is still non-negative, and then the value of the right-hand side of all constraints is also non-negative. If that is the case, then the current basis, so this current basis remains optimal. If that is not the case, then it means the current basis is no longer optimal. Okay, so this week we're going to look at 6 possible changes to the parameters in a linear programming problem. And let's start with the first change. Changing the objective function coefficient of a non-basic variable. We're going to perform the analysis on Dakota example. So here we are given the original problem for the Dakota example and then the optimal solution for that problem. What we are going to do here is that we are going to change the price of x2, which was originally 30, to becomes 30 plus delta. So delta is the amount of change that we're going to make. You may notice here that in the optimal solution of the original problem, x2 is a non-basic variable. So this is what is meant by changing the objective function coefficient of a non-basic variable. Now here's the summary of the formulas that we may use to construct the optimal table of a linear programming problem. Now if we change the price of x2 from 30 to become 30 plus delta, it means that we change C2, C without hat. C2 without hat, it is what we are changing here. And then if you notice that because x2 is a non-basic variables, it means that we are not changing CBV, And then we are not changing B inverse because what we change is in the objective function row. Remember that B inverse is something related to the constraints. So we don't change CBV because X2 is not a BV. We don't change B inverse. We don't change AJ because small a again is about the constraint. We don't change small b either because small b is about the right hand side of the constraint. So the only thing that we change here is just Cj, small c without the hat. Okay? It means that when we change C2, the effect will only happen specifically to C hat 2. In other words, when we change the coefficient of x2 in the problem, it will only affect the coefficient of x2 in the optimal table. And then we may see that the formula to compute C2 is this, C2 hat. And then we may say that the current basis remains optimal as long as the C2 hat greater than or equals to 0. Okay, so the change of the price of x2 will only affect the C hat 2. And then the current basis will remain optimal as long as C hat 2 is greater than or equal to 0. Now let's compute the effect of changing the price of x2 from 30 to 30 plus delta using the formula for C2 hat. So C2 hat equals CBVB inverse A2 minus C2. And then CBVB inverse does not change. So this is still 0, 10, and 10. And then A2 does not change either. So the only thing that is changing is C2 from originally 30 to become 30 plus delta. So we now obtain that our C hat 2 is 5 minus delta. And then we apply this requirement that the current basis remains optimal if C2 hat is greater than or equals to 0. So C2 hat greater than or equals to 0, and we know that C2 hat is 5 minus delta. So 5 minus delta greater than or equals to 0. Finally, we may say that as long as delta is less than or equal to 5, the current basis remains optimal. So from the previous slide, we've seen that the current basis remains optimal if delta is less than or equal to 5. In other words, we can say that C2, or the price of x2, as long as it is less than or equals to 35, then the current basis remains optimal. So how do I get the number 35? Well, because here it says 30 plus delta, and delta is allowed to be less than or equals to 5. We know that C2 itself is less than or equals to 35. Or in other words, because delta is less than or equal to 5, you can say that you can increase the price of x2 from 30 up to at most 5 above 30, which is 35. Okay, so that's how I get this result. Now, what happens if the price of x2 increases until more than 35? So from, let's say, if we set C2 equals 40, what happens? Well, from our previous conclusion, we know that if C2 is greater than 35, it means that the current basis is no longer optimal. What we need to do is that now we need to compute or recompute the new C2 hat. So CBVB inverse does not change, A2 does not change, but here you put the new C2, which is 40. Now you can see that the result is minus 5. It means now that we will have a non-basic variables with a negative coefficient. In the case of maximizations, of course, it shows that our solution now is no longer optimal. After you recompute the new C2 hat, you get the old table, but then you append the result for the coefficient of x2. You replace it with the one that you just recomputed. Okay, so here becomes -5. Everything else in this table is exactly the same with the original optimal table of the original problem. Okay, so you just put the new C2 hat here, -5. Okay, once you've done this, you may perform the simplex algorithm as usual, and you get the new optimal table with respect to the new price of x2, which is 40. If we look at the solution, it does make sense actually. In the old table, you see that x2 is a non-basic, which means that we do not produce any x2. But now in the new table, you see that because the price has increased up to 40, now we are producing x2 as many as 1.6 units. Okay, so that's how we perform the sensitivity analysis with respect to the first change, changing the objective function coefficient of a non-basic variable. Basically, you just need to check the new CJ hat for that non-basic j variable, which that the coefficient changes. So you just check whether the new CJ hat is still non-negative. If that is the case, then your current basis remains optimal. If it becomes negative, like this example, it means that your current basis is no longer optimal, and then you need to recompute the simplex. Don't forget to append this to the old optimal table, and then recalculate the simplex algorithm until you obtain the new optimal solution. Okay, so that's for the first change, and then in the next one, we're going to see how we're going to perform the second change. Thank you and see you on the next one.